green, blue, indigo and violet. Or white light consists of these 7 colors, and those arrangement gives us the man's name, Roy G. Biv. So remember his name. Even if you like him or not, you need to remember his name, Roy G. Biv. So Roy G. Biv, note that it is R for red, O for orange, Y for yellow. See the relationship? G for green, B blue, I for indigo, V for violet. So Roy G. Biv gives you the order of the white light's colors from higher wavelength to smaller wavelength. Remember this, because there will be questions on which one has the higher wavelength, which one has the lower wavelength, or I will give you a couple of colors and you may have to arrange them in the order of higher wavelength to lower wavelength, things like that. Okay? So you can do all those kinds of problems by remembering just this name, Roy J. Biv. And remember, that is from high to low. That is how it is arranged. Now, we've heard that light has dual nature, or light exists as waves and particles. You just have only this, just this background information. You are not going to go into the details of all this. These things go very, very deep into physics and chemistry, okay? We are not going to go for any of those deeper stuff here. It's just for kind of, a touch, just a superficial knowledge of the words. That's all you are looking for. So light exists as both waves and particles. Now we already talked about waves. The wavelength and frequency both are constituents of waves. Now when we say light exists as particles, you can think of that as packets of light, okay, small packets of light, and we call those packets with a special name photons. Photo, the word comes from photoelectric effect, photo, it all comes from that word, the packet nature of, or the particle nature of light. So we call it photons, and once again the characteristics of waves are frequency and wavelength, and that equation given after that, C is equal to lambda nu. C represents the speed of light. C always represents the constant speed of light, 3 into 10 to the power 8 meter per second. And C is equal to lambda nu. Lambda is the wavelength, nu is the frequency. So the wave nature of light, if you know that equation, then you can derive whatever is given, whatever is missing, all those things. Now we are going to look into the photons. How do we characterize photons, or how do we come up with an equation? Now energy of a photon is directly proportional to the frequency and inversely proportional to the wavelength. Well, we already know that wavelength and frequency are inversely proportional to each other. So if photon is directly proportional to frequency, then it has to be inversely proportional to wavelength, right? So that is what it says. Energy is directly proportional to frequency and inversely proportional to the wavelength. Using, yes?
What does the H stand for again?
H is Planck's constant. Just coming down further. So the energy of a photon can be represented as E photon. That E photon represents energy of photon, and that can be expressed using this relationships, hc by lambda. H stands for the scientist Max Planck's, it comes from the name Max Planck. H is called Planck's constant, which is 6.626 into 10 to the power negative 34 joules second. You don't have to memorize that number. If I ask you to do a calculation, I will give you that constant. Okay? You do not have to memorize it. H stands for Planck's constant, C for speed of light, lambda for, what is lambda? Wavelength. Lambda is wavelength, nu is frequency. So look at the first equation. C is lambda nu. So if I rearrange this equation, let me get the pen, and so if I rearrange this equation for nu, I can write that as C by lambda, right? So in this equation, if you substitute this C by lambda by nu, then you get H nu. They are one and the same. Why both are given? If you are given lambda in your problem, then you can use this equation, Hc by lambda, because H and C are constants. H is Planck's constant, C is speed of light. If wavelength is not given, then you can, if frequency is given, then you can use this equation, H nu. That is why both are given. And I've just shown you how you get, they both are one and the same. Because here the C by lambda is nu. That is, rearranging this equation you get nu is C by lambda. Okay, now we talked about frequency. Frequency is number of waves that pass through one single point in 1 second. Here are two different lights from two different laser lamps, red light and green light. What do you think? Which one has greater wavelength? Which one has greater frequency? First let us concentrate on frequency. Which one has greater frequency? The green light, because shorter waves. So if you take this one point, many waves will pass through, the green waves will pass through in 1 second, right? Whereas red is very long, so less number of waves will pass through. That answers your next question. So which one has greater wavelength? Red has greater wavelength, right? Okay, so you can represent the wavelength and you can recognize wavelength and frequency. And otherwise also, if you recognize which one has greater frequency, then you know that frequency and wavelength are inversely proportional. Therefore, the other one should have greater wavelength. Whichever way you think it works. Okay, so now we are going to look into the atomic spectra. So why we talked about the spectrum of light, different colors, frequency, all that is, when we look into atomic spectra, we are going to see like lines, or waves, and we need to understand why we get that or how we get that. That's why we just talked a little bit about the electromagnetic radiation. Our main goal is to understand the atomic structure. That's what we are going to look into now. So when visible light passes through a spectrum, we know that its components separate into all those colors, and white light gives something called a continuous spectrum. As the word suggests, what do we mean by continuous spectrum? Here is the white light spectrum. If you start from the lower wavelength, violet region to red, do you see any gaps in between? You don't. When one color is over, the other color starts, and then the other color like that, right? All those 7 colors, they are continuous. They are kind of overlapping, and then you get the next one, it goes like that. There are no gaps in between. But if you take the spectrum of colored light, such as the light which comes from a neon lamp, you don't see continuous spectrum. You see only light or the colors in particular region. Like the first one, these 3 gives spectrum of 3 different elements. First one is mercury. If you take the spectrum of mercury, you will see a line here, then a line here, then a couple of lines here. Rest of it is all black. Again for SR, strontium, again different lines. Neon, different lines in different places. These are not continuous, right? We see so much gap in between. We see colors only as lines in particular region. So these type of spectra are called line spectra. As the word suggests, since you see only particular lines, we call this line spectra. And the visible light, which is continuous, no gap, we call it continuous spectra. Okay? So white light gives you continuous spectra, whereas elements give you line spectra. Now, how do you produce line spectrum? You don't need to learn that, but it's just the spectrum is produced when an element has been heated or subjected to an electric charge. So usually you heat an element and then let it cool down. While it is cooling down, you have instruments called atomic spectroscopes, and they will do the analysis. You don't have to worry about that, and it will produce the spectrum also and give you on your computer screen. We have instruments which does that. But what we are going to concentrate on is, why do only certain lines appear and what causes the specific colors of lights to be emitted. Now, I can tell you one more thing. If you take the line spectra of all those elements in the periodic table, no two spectra will look alike. At least there will be a mismatch of one line. Okay? No two spectra will look alike if you take the light spectra of every element in the periodic table. So this is called, the line spectra actually are called fingerprints of elements. Just like in humans, no two fingerprints are the same. If you take the line spectra of every element, no two are going to be the same. So we call it fingerprints of the elements, atomic line spectra. Now, why we are going to see why only the certain lights appear for each of them and what causes these specific colors to be emitted rather than kind of a continuous spectrum. So that brings us to the first model we are going to learn. This model, by learning this model, it will kind of explain to us why we see the specific lines. It's called the Bohr model of hydrogen atom. Bohr comes from the scientist named Niels Bohr. So we gave his name because he is the one first came up with this atomic spectra explanation. So the hydrogen spectrum, if we take hydrogen spectrum, the first element, and if you take an atomic spectra, you will see just 4 lines on the hydrogen spectrum. You can see 4 lines. It's marked for you. One at 410 nanometers, then another one at 434, then 486 and 656. Okay? So Max Planck, that guy's name which I just showed you, I told you a few minutes ago, the H, Planck's constant, that guy. So Max Planck first made a hypothesis, like people were trying to figure out why this line spectra exist and why are they like fingerprints, why they are not the same for couple of elements or at least 2 elements. So first this guy Max Planck hypothesized that energy produced by atoms can have only certain values and they can be quantized. That means each atom's whatever energy is produced, it's kind of special to each element, and we can actually calculate that or we can quantize that. And that is the reason why only distinct lines are seen in elements' line spectra. So that's what he said. And we represent all those energy. You learned already about wavelength and frequency. We can represent the energy using either wavelength or frequency. So line spectra usually uses wavelength. That is why the units are in nanometers. And the energy can exist only at certain wavelength. So you will see only colored specific to that particular wavelength. That's what the hypothesis was. But that didn't explain everything well. So Niels Bohr, he was a student of Rutherford. Remember Rutherford? Have you heard that name before? Yes, you have. In chapter 2 when we talked about the discovery of nucleus, protons, electrons, neutrons, all that stuff, Rutherford was one of the scientists who was involved in those discovery and somebody who actually came up with that plum pudding model. Remember all those things from chapter 2? So that was Rutherford. So Niels Bohr was a student of Rutherford and he studied the line spectra of hydrogen atom to understand the electrons in the nuclear model of the atom. So Rutherford had the nuclear model, but still, Niels Bohr was further studying on that. So Bohr came up with this planetary model in which electrons orbit the nucleus in circular pathways. Well, from the nuclear model we know that nucleus is in the center of an atom. It has electrons and neutrons inside, and sorry, I misspoke. Nucleus is in the center of the atom. What is inside the nucleus? Protons and neutrons are inside the nucleus and electrons are outside, right? That's all we knew. But Niels Bohr said the electrons are outside, okay, but they are not just outside. They have the specific pathways called orbits, okay? The circular pathways. Planetary model, because we all know our planetary model, like our Earth is on the solar system where sun is in the middle and the planets surround sun in specific paths. We call it orbits, right? Same type of model. So his model again was based on Max Planck's idea. Now when you look at this picture, it makes more sense. So here, this was his model. Say for hydrogen, he said nucleus is right here in the middle, okay? Then remember that hydrogen has only one electron, but what the model he is trying to show is outside the nucleus of every element you will find this circular pathways. So many circular pathways. Okay? Now, and the specific things about this circular pathways, we call this each of these pathways as n is equal to 1. N is the designation for those pathways, orbits, and we just number them 1, 2, 3, 4, 5, 6, so on. 1 is closer to the nucleus, that is, as you can see, this is nucleus. The first pathway is 1, the second pathway is 2, the third pathway is 3, so on. Okay? Just understand this concept, just like the solar system. And then one more thing is the energy. Energy increases as its distance from the nucleus increase. So as we come out like this, 1, 2, 3, 4, 5, 6, we are increasing its energy. Or 1 has the lowest energy, 2 has little more than 1, 3 has more energy than 1 and 2, 4 has higher, like that. Everyone got the picture? So we have nucleus, just for every element, okay? You have nucleus, outside you have these orbits, and each orbit as a distance away from the nucleus, its energy is increasing. Okay? That's the model. Now, what we are going to do is, we are going to place the one electron in various orbits. So, hydrogen has just one electron. Let's imagine first that electron is on the 6th orbit, okay, right here. Then that electron decided to jump from 6 to 2. That's what this arrow shows. Just focus on, maybe I should make a different ink so that you can actually see where I am pointing. So this is what I am focusing right now, the first electron right here on N6, and this guy decided to jump to N2. Okay? What did we talk about energy? 6 has more energy or 2 has more energy? 6 has more energy, right? 2 has less energy. So he was here on 6 with a very high energy. Now he jumps to 2. What happens to the difference of energy? That difference of energy is emitted as light, in the form of light. Light is a form of energy, right? It can be emitted as heat or light or any other electromagnetic radiation. But when electrons jump from orbit to orbit in elements, what happens is the difference in energy is emitted as light. And whatever is that amount of light, you can quantize that using wavelength. If you quantize that, that energy will fall into that, that energy will fall into exactly right here at 410. So you will see a violet line right there just for that amount of energy. Now let's think about, let's imagine that, what? I think by mistake I did scratch. Okay. So now let's think about, let's say our electron is, okay guys, my pen is acting weird. So let's say our electron is in n is equal to 5 right here. Okay. Again, after some time he got bored, decided to jump to n is equal to 2. Once again there is an energy difference, right? 5 has higher energy than 2. But this difference of energy is lesser than this difference of energy, right? You can see that by the length of the arrow, or you can, that concept, that is why the arrow is shown here, but you have to get that concept. As we go away from nucleus, energy is increasing, right? So 6 has the highest energy, from there somebody is jumping to 2, and 5 which has higher energy but not as much as 6, somebody is jumping from there also to 2, so the difference of energy here is lesser than the first case. So when that much energy is released as light, that will show up at 434. Now next case, when n is equal to 4, electron is right here, jump to 2, corresponding energy is right here at 486. Now let's see, the electron was in 3, jump to 2, the corresponding energy shows up at 656. So whenever electrons jump from this orbit to orbit, the difference of energy shows up as lines, and for every element that energy emitted when an electron jumps from one orbit to another orbit is different. That is why the line spectra of every element is different. So Niels Bohr said this is the case, and that is why we see only specific lines in an element spectra, not a continuous line. Now, as I just told you, when electrons move from the higher energy orbit to the lower energy orbit, it loses energy equal to that difference, and the energy difference can be represented like this: E final minus E initial. So E final is where the electron ends up, and E initial was where the electron was in the beginning. So whatever the difference, that released as an energy, and that energy is actually released as photons. We said that light has dual nature, either as photons or as waves, right? So when this happens, usually the energy light is released in the form of photons. So energy of a photon equals to this difference of energy between the two orbitals. So this is the Bohr model. Okay. There were a lot of deficiencies in Bohr model. That is, it explains only the hydrogen atom and its spectrum. Bohr could do a very good explanation of hydrogen atom, just like I did now. The orbits, jumping, difference of energy, light. Good. Everyone understood that. But then what happens to, let's say, something like manganese, which has 25 electrons? Is it possible to keep track of 25 of them, where they are every time, where they are jumping every time? You know, it becomes really difficult, right? You can imagine, like, you know, you just have one kid to kind of play around, you can keep track of him, but if it's in a play school, you are there with 25 children and you are just one person. Wow, right? Everyone is running around all the time. Can you just keep track of every single one of them for every single second? No, you cannot. Same thing here. If you have only one electron, like hydrogen, it was so easy, explained well, but when you have so many electrons, it's really difficult to keep track of everyone's jumping from orbits to orbits, right? So a different model or a more complex model was needed, and that gives us to the modern model of atoms, which we will look into next section. But Bohr's model did give insight into the quantized behavior of the atom that was later better understood. As I said, when we talk about the modern model, we will understand that better. That is, when you have multi-electron atoms, how do we keep track of it, or how do they produce spectra? Okay? But that was from Bohr's model. He put the basement. From there we build on the modern model. Okay. So Bohr's model is clear for everyone. That was just the planetary model. Nucleus as the sun in the middle. Then you have orbits. As we go away, the energy is higher. And when electrons jump from a higher level to lower level, whatever the difference of energy is, that is released as photons, and the line spectra will show at that particular photon how much energy it has. It will show at that light. Okay, let's do a question, a clicker question before we go for the modern model. Ready? Here is your clicker question. Very simple one. Read carefully and choose the right answer. In the Bohr model, which one of the following electron transitions in a hydrogen atom result in the emission of light with the highest energy photon? So think about Bohr model. What did we just say? Everyone has clickers today? Okay. We'll stop at 1:30. Be before that. Okay, I think I counted 19. Everyone answered, right? No? Okay. Which one? 63. What did we say? The higher we go, the farther we go, higher the energy is, right? And electrons jump from high energy to low energy. That is when the light is emitted, not from low energy to high energy. If somebody is in the low energy, if somebody wants to go high energy, you have to provide energy. Okay? So the correct answer is A, N is 63. Okay, what happened? I thought that was a sure shot one. D, there is no chance, guys. 3 and 5. When you have 6 and 3 there, you don't have to consider 3 and 5. Now the question was highest energy photon. So as we talked in the previous example, high energy to low energy. That's what happens. Not from low energy to high energy. So that eliminates C also. All right. Now we are going to look into the modern model of atom. So the Bohr's model, of course, was 200-year-old, and that developed the modern model which is currently in practice. We are going to develop that now. So the modern model of atom is based on Schrodinger's mathematical model of waves. Consider yourself lucky that you do not have to learn the wave equations. It's a 2-page equation, derivation of the Schrodinger's mathematical model of waves. Okay? So we are lucky that we don't have to look into that. So we are just going to take what is the points we need to learn from that. We are not going to go into the mathematical derivation of this modern model. So modern model talks about electrons as occupying orbitals, not orbits. So there is a difference between the two words, orbits and orbital. Orbits, just like in the solar system, you have those circular pathways. Okay? It is fixed, just like Earth's orbit. It can only move in that direction. It cannot move away from that or from, away from both directions. Right? It has to stay on that. And that is controlled by, of course, the gravity and all that stuff. But you just think about that. But orbitals are, it's not just fixed circular pathways. These are three-dimensional regions in space where electrons are likely to be found. Not just a circular pathway. So you cannot say the electron is now, just Bohr said, electrons are on, those circular pathways. But we later understood that electrons are not just sitting on a circular pathway. There is a region in space, a three-dimensional region in space, where the probability of finding an electron is more. That is called an orbital. So, say for example, if you look at the picture given there, we would generally, in the bottom, we would generally represent an orbital. This is an s orbital, which we will learn the names and all that in next slides. So we will represent the orbital with, the circular three-dimensional space. So it is like a ball now. It's not just a circle, because now it is three-dimensional, right? Now, if you look at the first picture A, you see a lot of dots. The circle is, or that ball is made of lot of dots. In the middle you see the dots are really close together. So this you can think of as the probability. This comes from the probability theory. So the probability of finding the electron. Where will you find the electron? Where the dots are close together, the probability of finding the electron is better. Or the electrons spend more time in that closed region, that dot closed region. Whereas the dots are spread means the probability of finding an electron there is lesser than the middle region. Okay? So orbitals means three-dimensional spaces or regions in space. Now principal energy level, this is another word. The principal energy level means orbitals of same size. Don't worry, it will become clear to you when we do more. So this was Bohr's diagram. Now we are connecting that to the modern model. So orbitals of similar size exist in the same principal energy level. So the only one thing which we are carry forward from the Bohr model is that n is equal to 1, n is equal to 2, n is equal to 3, that part. Bohr said each of these circular pathways, when it is moving away from nucleus, we call it n is equal to 1, n is equal to 2, so on. In the modern model also, as we go up in energy, we get this different levels, and each of those levels are also called n is equal to 1, n is equal to 2, so on. And as you can see, 1 is the lowest energy, 2 has the higher energy, 3 has the next energy, 4 has the next energy, so on. Can anyone see one more difference in Bohr's model and this energy graph? In Bohr's model, look at the, the difference between, the distance between the lines. They were kind of uniform, right? Yeah, as we move further, we see a little bit increasing, but otherwise also they are kind of increasing in a proportional pattern. But in the modern model, we know that that's not the case. The energy gap between 1 and 2 is huge, then 2 and 3 is not much. As we go further, like 4, 5 and 6, they become so close together, not like what you see in the Bohr model. Okay? So this is the new energy level. But we still call each level a principal energy level, and it is labeled by n, just like Bohr did. Now, we talked about orbitals, which are three-dimensional spaces. There are 4 general types of orbitals. These are important, guys. Now onwards, really pay attention. You need to learn a lot of things. The modern model consists, there are no problems as such, but there are a lot of concepts to learn. Okay. So there are 4 general types of orbitals and the names are S, P, D and F. Don't ask me why we chose only those 4 letters. Okay. So we call them S, P, D and F. 4 different orbitals. Here is just a picture of each of them. Like an S orbital we have seen before, like a ball. These things are given there to give you the idea of 3 dimension. Okay. And then there is a P orbital like this. It has like 2 lobes. You can imagine like if you take 2 balloons, like long balloons, and just hold them in the middle in your hand. How do they stand? Both lobes goes into both sides. A P orbital will look like that. Now D orbital, let's say you are holding 4 of them now, or an F orbital, how many you have there? Yeah, well 3 and 1 has 4, so you are holding like 7 of them, right? Anyway, that was just try to get you an idea, but it's not balloons, it's not like that, it's just so here the typical representation of an S orbital, as I said, S orbital is the ball shaped orbital, the round shaped, and as the principal energy level increase, the orbital extend further from the nucleus. That point comes again from the Bohr model. As we go further from nucleus, the energy is increasing. So if you look at the first 3 S orbitals, in the first level the S orbital is really small, in the second level S orbital is large, showing that it is distance from the nucleus is increased. And when it comes to 3s, remember each of them in the middle you have the nucleus, the dot, right? So the bigger the ball is, higher the energy is, and farther away it is from the nucleus. Now if you look into P orbitals, there are 3 P orbitals in a sub-level. So P is one kind of orbital, but there can be 3 different sub-levels in P. We know that usually when we represent space, the 3 dimensions in mathematics, you use x, y, z plane, right? X plane, y plane and z plane. Those are the geometric coordinates. So in each plane you have a P orbital. That is, as you see, the first in the z plane, so it goes through like this in the z plane, so that is called a 2pz. Then the one which lie on the x plane, we call it a 2px, and the one which lie on the y plane is a 2py. Okay, so 2px, py and pz, 3 of the P orbitals. Then P orbitals can overlap with their centers at the nucleus. So if you hold all of them together, as I said, if you keep 3 pairs of balloons in your hand, how would it look like? Your hand will be the nucleus, and the 3 pairs which are moving away from your hand, those are the 3 different P orbitals. Okay, you can visualize in that way. So your hand is right here in the middle, and you have 3 pairs. That means there are 6 balloons in all directions. Then there are 5 D orbitals. So D can have 5 sublevels. You don't have to memorize those names like dyz, dxz, dxy, x square minus y square or dz square. You don't have to memorize those. All you need to remember is D has 5 levels. Okay? Among these, my personal favorite is the last one, balloons in the donut. And there are 7 F orbitals. So, let me summarize what we just see. So, we have 4 different types of orbitals. We call it S. Oh, I need to change the pen color. Otherwise, you won't be able to see it clearly. Okay. And okay. So we have 4 different types of orbitals. We call it S, P, D and F. Okay, that is the first step. Now, S we have only one type, P we have 3 types, D we have 5 types, F we have 7 types. That's what we just said. Can you start getting the concept now? Remember that order, S, P, D, F. Then, how do you remember those numbers? The odd numbers, right? 1, 3, 5, 7. Those are, if you start with the odd numbers 1, that is how it goes, right? So make this picture in your mind when I am writing this. S, P, D, F, each of them, write the odd numbers, S being the 1, the number below each of them. That many types are there in each of them. Easy to remember when you think in this way? Rather than just reading everything and trying to, oh my God, how am I going to keep track? No, this is easy, right? SPDF and the odd numbers. So that many types are there in each of them. We are going to add more into this, okay? But first get this concept. Okay. Now, so this kind of again in words it is explaining it. So the first principal energy level, now we are going to add that n values also to our picture. Okay? So the first energy level n is equal to 1, you have only an s orbital. When it comes to n is equal to 2, you have an s and a p. When it comes to n is equal to 3, you have an s, p and a d. When it comes to n is equal to 4, you have s, p, d and f. It goes in that order. Okay? Now, let me get a screen and put all this into what we just said. So, I said we have, well, now this should be written as, okay, I'm going to write the n values first, okay? 1, 2, 3, 4. Okay? Now, when n is equal to 1, you have only an s orbital, the first orbital. Okay? When n is equal to 2, you have an s and a p. Remember the 4 orbitals, that is where we start. S, P, D, F, right? So, when n is equal to 2, you have S and P, 2 of them. When n is equal to 3, you have S, P and D, 3 of them. When n is equal to 4, you have all 4 or S, P, D and F. This is one point, okay? One concept, that is the number of n, that also represents how many, what types of orbital you have in each level. When n is equal to 1, you have only s orbital, the first type. When n is equal to 2, you have first and second type of orbital, s and p. When n is equal to 3, you have s, p and d. When n is equal to 4, you have s, p, d and f. Right? This is one. Now, each of these s orbitals, how many sublevels are there in an s orbital? 1. Remember that odd number we wrote? That represents the sublevels. Okay? S has only one sublevel, P has 3 sublevels, D has 5 sublevels, F has 7 sublevels. If you remember this much, it becomes so easy for you when you write the configurations. This is the fundamentals of writing electronic configurations. Yes?
The N stand for nanometers?
No, N stands for principal energy level. Is everyone with me so far? These two things are connecting. You can be clear on this? Okay. So, having said this, we are ready to write the orbital diagrams. So, what are orbital diagrams? Orbital diagrams show the sublevels and orbitals that can exist at each principal energy level, and each box represents an orbital, and group of boxes are representing the sublevel. So, we know that when n is equal to 1, you have only an s orbital, right? And s orbital can have how many sublevels? Just one, the first odd number. That is what this picture shows in the bottom. N is equal to 1, you have only an s orbital, and each box represents the sublevel. Now you come to n is equal to 2. When n is equal to 2, what types of orbitals you have? S and P. S can have only one sublevel, therefore one box. Oops. Therefore one box, whereas P can have how many sublevels? 3. Therefore you have 3 boxes there. Now when it comes to n is equal to 3, what are the types of orbitals you can have? S, P and D. S can have again only one sublevel. P can have 3 sublevels. How many sublevels D will have? 5. Therefore you see 5 boxes. Make sense? We are connecting those two things we just discussed, right? So as the n number increase, remember to add each type also. S, n is equal to 2, S and P, 3, SP and D, like that. Now you guys tell me, if I have n is equal to 4 here, what do I see? Just tell me the number of boxes and types. What types I will see if n is equal to 4? All 4 types, S, P, D and F. Now tell me, under S how many boxes I will see? Under P how many boxes I will see? For D? For F? 7. Good. So in hydrogen atom only, the sublevels within principal energy level have all the same energy. That means if you look into each n level, let's say for example n is equal to 3, this is the energy level, and you see that the S, P and D, they are all at the same level, right? Or in other words, we are saying at n is equal to 3, S, P and D, they all have the same energy. But that happens only in hydrogen atom. In multi-electron atoms, the sublevels vary in energy. Okay, they are not of the same energy, and this is how the energy is increasing, the same order, SPDF order. S is the lowest in energy, P has little bit more energy than S, D has higher energy than P, and F has the highest energy. Okay, that is within each n value. So say for example, if you have n is equal to 3, you have 3S, 3P and 3D. Among those 3, S will be lower energy, P will be next and D will be next. Okay, so we are adding each level of concept into what we already know. So that is the way the energy vary from them. Now we are going to look into, we are ready to write, or we are ready to see the arrangement of electrons. We know enough background now. So now we are going to see how are electrons arranged in an atom, and whenever we consider this electronic arrangement of atoms, we will consider only the ground state. Ground state means the lowest energy state or the most stable arrangement. So whenever a question is there or whenever we talk about electronic arrangement, you just assume that you are talking things at ground state. Okay? So Here is an example. Let's say we take carbon. How many electrons carbon has? Don't look in here. How do we figure out how many electrons carbon has? From the periodic table, yes. So, how many electrons carbon has? 6 electrons, because it has atomic number 6. Therefore, it has 6 electrons. Now, we are going to see how the electrons are actually arranged in the atom, or in which sublevel, which orbitals those electrons reside. So, we know that S is the lowest energy level, right? So, when n is equal to 1, you just have a 1s orbital. 2 electrons will go into one box. That is the limit. Each box can take only 2 electrons. Okay, that never changes. Now, when 2 electrons goes into a box also, they have to be represented as up and down arrow. One is up, then the other one is down. This is the way you represent electrons. So that means each of these arrows in those boxes represents the electrons. That is how we are going to represent electrons now. Okay? So carbon has 6 electrons. As I said, we are assuming that this is the ground state or the most stable state. So we start with the lowest possible energy. In the principal energy level, the lowest possible level is n is equal to 1, right? Because when we go further, n is equal to 2, n is equal to 3, we are increasing in energy. So n is equal to 1 is the lowest possible state. Now when n is equal to 1, you have only an s orbital. So that is the box given here, the 1s orbital. 2 electrons in there. We have how many more electrons to show? 4 more. So we go to the next level. N is equal to 2. N is equal to 2, we have s and p orbitals, right? Each box can take 2. We start with the lowest. Among s and p, which one has lower energy? S has lower energy. Remember, energy also increase in that way, s, p, d, f, in that order. So among 2s and 2p, 2s has lower energy, so 2 of them will go in here. Now we come to 2p, we have 3 boxes and we have 2 electrons left, right? Carbon has 6, so far we have showing 4, so we have 2 more. So we are going to put them into the 2p boxes and 1 electron goes into each box or the first 2 boxes, then you are done. You don't have any more electrons, so we are not going to put anything on the 3rd box. Now, here is a question. Keep it in mind. We are going to answer it later. Why these 2 electrons in the p level did not take the first box like this, up and down? Okay? Why did they go to separate boxes? Hold on to that thought. So, electrons occupy the lowest energy orbitals first. We said that electrons will go from the lowest energy, and actually that is called the Bohr principle. That statement, or electrons goes to the lowest energy, that is called Bohr principle. And then we also said that only 2 electrons can go in one box, or in other words, no more than 2 electrons occupy each orbital. That is called Pauli exclusion principle. And the 2 electrons in the same orbital must have opposite spins, and that is why we write up and down arrow. They are opposite in spins. This spin comes from the magnetic field. Again, you are not going into the details, guys, so just kind of know the rules as simple as this. Okay? Don't think too much about what do you mean by spin. You don't want to know. This itself is enough confusion for you. So just remember, electrons occupy 2 only in one box. They have to be on up and down arrows. Okay, that's what it says. And they start with the lowest energy first. So now if you take helium's orbital or helium's diagram, Helium has how many electrons? 2. Helium is atomic number 2. So 2 electrons. So we'll start with the lowest energy level possible, the 1s. And 1s is lower in energy than 2s. Right? So both the electrons will stay in 1s. And that is why we have in the 1s box 2 of them. So now if we take the third element, lithium, the third electron comes, no more space in 1s, so it will go to the next level, which is the n is equal to 2 level, and n is equal to 2, you have s and p. Among s and p, s is lower in energy, so it will take the s orbital. Now can you predict when the next one, beryllium, with 4 electrons, where do the 4th electron go? Same with this box, but how would it end up? It would end up with a down arrow. Good. So that is boron. Boron or beryllium, guys? What is number 4? Boron is, okay, this is showing 5. I'm sorry. Then they are missing beryllium. They are not even showing beryllium. Okay. So boron, there are 5. So after the 4, when the 5th one comes, it will go to 2p, first box. And then again we are looking into carbon. And I said instead of coming here as a down arrow, it went to the next box and hold on to that thought. As it says, why do the electrons in the p sublevel occupy separate orbitals? Before you read the next rule, let me tell you this. Let's imagine we are going on a trip, okay, on a bus, on the first day of our class. So what does that mean is you don't know anyone else. You are all perfect strangers. Let's imagine that. And we are going on a trip. What is the human tendency when you get into the bus, when you sit on the seats? What? Yes, pick one is empty, or everyone will try to go pick one is empty, right? Now let's say the bus has only 15 rows, 16 rows, 8 on each. First 16 people got into the 16 seats. What happens to the 17th person? No option, but the person has to sit with someone else, right? And when the person, when you are perfect strangers, when someone sits next to you, you're not going to sit there like that. You know that you guys are going to stay there for some time. It's a long trip. So you might say, oh, okay, hello, I'm just, what's your name, or you might introduce yourself, talk to each other, right? But that takes a little bit effort, right? To start talking to a perfect stranger and, becoming friends with each other. Same thing happens with electrons. If there are choices, like same energy, they would all like to sit in the window seat first. That is why when there are 2 electrons, but 3 empty boxes with same energy available, they pick up the window seats. Once all 3 is filled, the other guy comes, he has no option but to sit with someone else. And it takes a little bit of effort. And that's what we call, it takes a little bit of energy to pair up the electrons. The effort you are doing, electrons needs that little bit energy to pair up. Okay? And they do not want to spend any energy, just like us. We would just like to, most of the time, we would just like to be in our own universe. So, they don't want to spend that energy if need be. We are going to. So this rule which says if there are same levels, electrons will take the window seats first, then only they will pair up. That rule is called Hund's rule. Okay. So if you look into further, after carbon, we'll look into the pictures again after the slide. So this one is kind of now summarizing the rules, the 2 principles and 1 rule determine how the electrons are filled. Now all three are given there. So off-Bohr principle, which says electrons fill orbitals with the lowest energy first. Then Pauli exclusion principle, which says electrons can occupy, like 2 electrons only can sit in one box and they must have opposite arrows. And the third rule, which we just talked about, they will take the window seats first if available, and then only they'll pair up. Okay, so those are the 3 rules, or 2 principles and 1 rule to remember. So let's look further. This was carbon. They are not showing us further now. Anyway, this is what we have seen first. The 1s, 2s and 2p. It will be difficult all the time for you to draw these lines and boxes, right? So now we are going to kind of make it simple, like what is showing in the bottom. We'll just put the boxes all in the same level, because it is understood that as we go further the energy is increasing, and we'll just write what each box is, like 1s, 2s, 2p and so on. Let's say even that becomes tedious after some time. Still you have to draw the boxes. So we come up with a shorthand notation. We will write the electron configurations, like we write the number of the principal energy level first, then we write the symbol of the orbital like sp, d or f, and then we use a superscript on the right side to represent the number of electrons in each of them. So say for example this was carbon, 1 represents the principal energy level, n is equal to 1, s is the orbital, it has 2 electrons, so we write 1s2. Then comes the next box, 2s, it has 2 electrons, so we write 2s2. Then comes the 2p level, it has only 2 electrons in carbon, so we write 2p2. These superscripts represents the electrons, so those numbers should add up to the total number of electrons. Carbon has 6, 2 plus 2 plus 2 is 6. Okay, so this is how we are going to write the electronic configuration. It cannot go much simpler than this right now. Okay, so we are going to learn this for to write this for every element. So here is the picture showing elements in period 1 and 2, that is hydrogen to neon if you are writing the box, and then if you are writing the shorthand. So we had seen up to carbon here like this. Remember, for nitrogen, when you have 3 p, they'll take all window seats, and then comes oxygen. Now then extra one have no other option but to pair up with the first one. Then for fluorine, the other guy also will pair up, and in neon everyone is paired up. The bus is full. Okay? So use the orbital diagram to write electron configuration for silicon. Okay, so I'm going to take you through the steps. How do we do this? First, you need to know how many total electrons you have. Silicon, how many total electrons you have? 14 from the periodic table. Okay, so we have to show all 14, but you have to keep in mind we are following those 3 rules we learned. We start with the lowest energy first. That means, where do I start? I start at the 1s. How many electrons can go in 1s? 2. How do I write them? Up and down arrows. Okay. Next please. I come to 2s. How many? How many I have total? 14. I have to show for 14. So I have shown 4. I have to keep going, right? Okay. Next level comes 2p. The way they fill is 1, 2, 3 first and then they pair up. How many electrons am I showing so far? 6 plus 2, 8 plus 2, 10. Am I done yet? No, keep going. So at the 3s level, how many will go? 2. So now how many I have shown? 12. I have 2 more. Tell me how they fill up. 1 in 1 box. This will be the electronic arrangement of silicon. Okay. Aren't they giving any more practice? No, probably later. Yes. Oh, okay. That's fine. We'll just look into this. Let me see what else I have ahead. Okay. You know, guys, I'll stop here, Cody. I just thought they are going to give us some more examples maybe after this, but not right now. So your homework is due today, okay? People who walked in late, you can collect the exam from me